Hola, we're in 9.3, part 2. We've seen all kinds of work with radicals, so now we're going to see why we would need to use that. We're going to take a look at some geometric or trig, I don't know which one you want to call it. It kind of falls into both categories, working with triangles. So let's talk about what a triangle is, what kind of triangles we have. What kind of triangles do you know? Well, you can't answer me, so I'm going to answer for you. We have acute. Okay? That's where each angle is less than 90. Okay, and then we have obtuse, where one angle is more than 90. Okay, and the others are not. We have scalene triangles. That could be a scalene triangle. Let's just draw one out here. Okay, scalene means all angles and all sides are different. Then we have an isosceles. Isosceles, that is not spelled right, I don't think. Anyway, these two angles are the same, and these two sides are the same. Okay, then we have an equilateral, where all sides are the same and all angles are the same. Okay, I'm not going to spell that either, equilateral. And last but not least, we have a right triangle, which has exactly one 90-degree angle in it. That's the one we're going to be looking at. So remember, triangles are three-sided closed polygons. All angles inside all of these add to 180. And specifically, a right triangle has some pretty unique properties. So we have to go back in time into Pythagoras' time. He was a Greek mathematician way back when, who didn't invent the Pythagorean theorem, but they named it after him. But it's as old as he is. It's very, very old. How old? Well, what do you think? I like asking this in a classroom because people usually go, oh, 1600s, 1700s. Actually, Pythagoras, if you ever, I can't draw a picture of him, obviously. Pythagoras, he was around in 500 BC. So this is old stuff. This is mathematics that's 2,000–3,000 years old. I mean, this is the classic stuff. So what did he say? Well, he said in a right triangle, let's label what we have here. We have the 90. Okay, the side across here is called the hypotenuse. Okay, and that's always side C. And for right now, until we get into our right angle trig, we're just going to call these legs. And they're interchangeable. It doesn't matter which is which. This is the most important one, that the hypotenuse is always the angled side, and it sits across from the 90. Okay, so we'll call these A and B, leg A and leg B. Just so you know, the hypotenuse is always the longest in length. Okay, this side is always longer than those two. All right, Pythagoras, or someone thereabout, said that if you squared the length of the first leg and added it to the square of the length of the second leg, it's always equal to the length of the third leg squared. And so this became the Pythagorean theorem. Pythagorean theorem. Now, what's a theorem? Well, a theorem is a proven theory. And a theory is just something that you think is true. Okay, so if it's a theory, you go, yeah, it's looking like it's always true. And if you can prove it, this one happens to be an 81-page proof, but it is provable, which I am not going to do, then it becomes a theorem. So it's true for all right triangles. Is it true for equilaterals? No. Acutes? No. None of these, right? There's one case in which an isosceles happens to be a right, but only one case. And that's when these two are 45s. That means this one has to be a 90 up in here. So normally this only applies to right triangles, okay? So what this does for you is if you know two sides, whether it's the A and the B, or the A and the C, or the B and the C, you can always find the third side. Okay, so it's very important. So, you know, what was going on back in BC times? Well, they were building, um, you know, houses and buildings, and they were trying to get this. Let me try and make it a little bit more straighter. They were trying to get this to be perpendicular, so they had nice corners on their buildings, and they didn't know how to do that. So they would measure and measure, and then they'd measure this, and they'd put a rope across it right here. Where's my pen? And they would see if it worked, and then they could adjust it using this theorem. Or they were trying to get all their crops to grow straight, right? So they would use the Pythagorean theorem to stretch a rope from here to here and from here to here, and then calculate out what this needed to be and just tweak it until it was all perfect. And then they knew the crops were going straight. Okay, that's why sometimes if you look into the history, the Pythagoreans were rope stretchers. That's what they were called. And it actually turned into some sort of a cult later on in life. I think they're still around today. They just regard numbers as gods, and yeah. So I think they're related somehow to the Wiccans, but I'm not sure how. The Wiccans are also a group of people that look at numbers as deities and gods, and everything comes down to a number, and that's where the tarot cards come in play and all that kind of stuff. So anyway, I'm giving you way too much history here. So, but I think it's interesting. I'm a freak for the history of science. I think it's just fascinating how we came to be this technologically advanced with the science that we know and what it does for us. It's incredible, really, truly incredible. All right, so let's go back up here to see what we have going on. All right, we have A and B given to us, and we're looking for C. Well, that's pretty easy. So let's write down the Pythagorean theorem and fill in what we know. We know A is 12. We have 12 squared. We know B is 16. 16 squared, and that has to equal C squared. Well, let's add these two. Let's use a calculator. 12 squared plus 16 squared is 400. Yeah. So we have 400 is equal to C squared. Well, now we have a quadratic. Well, we can do one of two things. We can either, set this equal to 0 and factor and solve, or we could just get rid of the square by taking the square root, right? Because remember, the square root of a square is itself. So this side will become a C. But if I take the square root of that side, I have to take the square root of that side, right? And this is 20. Square root of 400, square root of the answer, which was 400, is 20. Now, I have an equation here. I should have the positive and negative values on here to be precise, but I can't have a negative length, so I have to disregard that negative, okay? Lengths on things have to be positive values. I can't have a length of negative 20. So my third side is 20. All right? Now some of these are going to come out to be, with radicals. Let's try this one. All right? First of all, we have to identify which sides we have. Okay, so if this is my 90 there, then this is my C. And this is my A and my B, or other way around, B and A. It's got to be this way. Okay, so C is equal to 11, and A is equal to 5, and B we don't know. So we're going to use the Pythagorean theorem again. A squared plus B squared equals C squared. Okay, so we have 5 squared plus B squared equals 11 squared, not 1. Well, what do we got? 5 squared is 25 plus B squared is equal to 121. 11 squared. I'm solving for B now. So I'm going to subtract my 25 across. So I have B squared is equal to, well, first of all, let's just make sure that we have 11 squared is 121, just so okay, and then we can subtract 25. I just want to be sure about all that. So we've got 96. Okay, Now I'm going to take the square root of both sides because I want to get rid of my square. The square root of a square is itself. And now I've got this 96 to deal with. Now I'm going back into 9.3 part 1 and saying, well, can I leave it like that? What are my rules and my radicals? I can't have a perfect square underneath there, right? So what were my perfect squares? Well, let's test out a 16. Is there a 16 in there? Let's see. Yep, there's a 16 in there. It's probably the biggest perfect square that I can find. So now I'm going to keep messing with this thing. All right, and I've got 16 times 6, and then I break it apart, and this comes out as 4 roots of 6. Okay, and the reason we do that is because it needs an exact answer that's simplified. I don't want a decimal, but I want a simplified radical. Simplified radicals are not easy, but we know how to do them, don't we? We sure do. Okay, so I'm not going to do very many of these. These are all done the same. You've got a ton of Pythagorean theorems in there. No, you don't. You only have 3. Okay. Okay, the next thing that we would need radicals for is distances between points. So this is all your Pythagorean theorem, your triangle work up in here. And another thing that we can use radicals for is distance. So if I would have a point, x1, y1, and another point, x2, y2, okay, this is designating, these are subscripts, it's my first point, my second point, and I want to know the distance between these two. I have a formula called the distance formula. And the distance between those two is the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay? So here I'm going to want to write down my points. Now it doesn't matter which one I say is 1 and 2. It's just completely random. But I'm going to put these on top here so that we really can see what we've got. And now I'm going to plug it into this formula. Do you see how x1 is 9, y1 is 10, x2 is 6, and y2 is 6. So I'm just plugging in values here. So x2 was 6 minus x1 is 9. y2 is 6 minus y1 is 10. Now I'm back into my radical rule, so I'm going to I have to keep in mind how to simplify. So 6 minus 9 is negative 3, and 6 minus 10 is negative 4, and negative 3 squared is 9, and negative 4 squared is 16. And 9 and 16 make 25, and the square root of 25 is 5. That one was really nice. I like it. So let's say, we were on a grid of some sort and each, was worth a foot or whatever. They'd be 5 feet apart. Right? So that's how the distance formula works. Let me see what else I have in here. Decimals, radicals. So I should probably do one of those, huh? Okay, so let's do the radicals. Okay, let's get it set up. We've got our x1, y1, our x2, y2. We've got the square root of 3, square root of 7, minus 3 roots of 3, 5 roots of 7. Okay? What does my distance formula tell me to do? It's going to tell me to take x2 minus x1. x2 minus x1. So I've got minus 3 roots of 3 minus root 3, right? x2 minus x1 squared plus y2 minus y1. So I've got here 5 roots of 7 minus root 7. And that should be squared as well. So that's your initial setup. You're just going to want to make sure that your points are all where they're supposed to be. You're going to want to slap it into the formula, and then you're going to want to start reducing down, right? So here we have negative 3 roots of 3 minus 1 root of 3 is minus 4 roots of 3 squared, right? And then we have 5 roots of 7 minus 1 root of 7 gives me 4 roots of 7, positive. And that's squared. All right. I'm squaring both of these pieces here. So the negative 4 squared is a positive 16. And a square of a radical, okay, so here, let me do this. Sometimes I have a hard time if I don't write everything down. This is the same as that. Okay, so this is your 16. This is a 3. The square root of a square is itself. Same thing here. We've got 4 squared for 16. 7, square root of 7 squared is 7. So let's see what kind of a number we have underneath there. Now I'm just going to use my calculator because I'm going to be really lazy. 16 times 3 plus 16 times 7. It's 160. Okay, now I'm going to go back into my radical rules and go, I probably got a perfect square sitting underneath there. And this one's pretty easy. I can see it right off the bat. 16 times 10, right? Split and evaluate. 4 roots of 10. That's how far apart those are. Well, let's see if that's correct. 4 roots of 10. Yep. All right, so again, you know, up to a certain point you can use the calculator. But then past that, this kind of stuff you can't turn that into this with a calculator. So you have to know how to do these by hand. All right, so let's do a couple of, I don't know how many of these I'm going to do. Probably none of them. There's only 3 here. But we have a color TV, and we've got this side, the dimensions, we've got the height, and we want to know what the diagonal is. Well, isn't that suspiciously like a triangle that's got a right angle in it? Yeah. Right? There's a right angle there. 18, 23.7, you're looking for the hypotenuse. All right, this time, since it's the nearest tenth, we're gonna, you know, like actually put that in the calculator, our final answer. The impedance of a parallel resonant circuit is determined as follow. Okay, so this is your impedance. This is your, what's E? Energy, resistance, omega, L. I don't know what these stand for. But you're just plugging this stuff in. You know, E goes there. 120 goes there. We're squaring that. Omega is 120 pi squared, the whole thing squared. And then we got L squared. Take the square root of all that and then divide. Okay? So this is just order of operations, really. You're just going to throw all these numbers in there. You're going to square this first, then you're going to square that and square that. Then you're going to multiply those two, and you're going to add them. Then you'll take the square root. Then you'll take E divided by whatever that number is. Okay? Don't forget that omega has 120 pi, so both the 120 and the pi get squared. So those will go in parentheses. And this one's really easy as well. We have a formula in the word verbal way. So it tells us to, if you want to find the distance to the horizon, like let's say, okay, so what this is doing is, let's say you're sitting on top of the, I don't know, on top of a building somewhere, okay? And here's your building, okay, and you're up here. and you can see the horizon, right? You can see that. So it depends on how high up you are. So it says to find the distance, that would be down in here, the distance to the horizon, take the square root of the height, however high you are. This time we're at 240. Okay, so we take the square root of the height, and we multiply that result by 1.224. Okay, so times 1.224. That's pretty easy. You know, we want to round to the nearest tenth, so we're not doing any kind of converting. We're just throwing that in the calculator, really. You know, square root of 240. So is that other one. That other one's a little more involved, but times 1.224. About 19 miles. Close to it. 18 point. Nope, that would be to the nearest tenth would be 19, wouldn't it? Should we try that? 19 miles. Yep. All right, that's it for the second part of 9.3. We kind of saw what we need our radicals for as far as Pythagorean theorem and distance formula and application problems. And then we'll continue on with 9.4. Just plowing our way through the stuff. So that's it for now.